Welcome to the LTE Advanced course. This course covers the enhancements developed by 3GPP in Release 10 and Release 11 to meet the International Mobile Telecommunications Advanced Requirements for the wireless. LTE Advanced enables peak target data rates in excess of 1 Gbps in the downlink and 500 Mbps in the uplink to be achieved. After completing this module, you will learn about Overview of Cellular Network Evolution, Brief Overview of LTE Release 8 Architecture, Description of LTE Advanced Requirements, Various LTE Advanced technology features introduced in Release 10 and Release 11, including Carrier Aggregation, Enhanced Multiple Input Multiple Output or MIMO support, Coordinated Multipoint or COMP transmission reception, Heterogeneous deployments, Relaying. So, let us begin. Cellular systems have come a long way since their introduction in the 1980s. The evolution has been from first-generation, 1G, technologies, beginning in the early 1990s, and eventually to current fourth-generation, 4G, technologies. As we discussed, during the evolution phases, technology has evolved to provide higher user speeds and better spectral efficiency to enhance the overall user experience and enable mobile broadband. First generation, 1G, radio networks were analog-based and limited to voice services capabilities only. 1G devices were easily susceptible to cloning and one channel supported only one device at a time. Global System for Mobile Communications, GSM, is 2G technology that offers both voice and limited data capabilities. GSM differs from 1G by using digital cellular technology and time division multiple access, TDMA, transmission methods. GSM offers data transmission rates of up to 9.6 kbps. General Packet Radio Service, GPRS, introduced the packet core network and the cellular network. 2G cellular technology combined with GPRS is described as 2.5G, that is, a technology between the second, 2G, and third, 3G, generations of mobile telephony. It provides moderate speed data transfer by using unused time division multiple access, TDMA, channels in, for example, the GSM system. GPRS offers practical data transmission rates of about 70 kbps. 3G, also called as UMTS, is developed by the 3GPP, third generation partnership project. In Release 99 was the first release of UMTS. It is characterized by change in access technology from TDMA to CDMA. UMTS Release 99 has a theoretical data rate of 2 Mbps, but the practical capacity is 384 kbps. UMTS offers packet-based transmission for text, digitized voice, video, and multimedia content. High-Speed Packet Access, HSPA, is a mobile telephony protocol that helps improve the performance of UMTS. HSPA is normally referred to as 3.5G, is developed by the 3GPP and is specified in its Release 5 and Release 6 document series, with minor enhancements described in Release 7. HSPA is an amalgamation of two mobile telephony protocols, High-Speed Downlink Packet Access, HSDPA, and High-Speed Uplink Packet Access, HSUPA, that extends and improves the performance of existing third-generation mobile telecommunication networks utilizing the WCDMA protocols. The first HSPA specifications supported increased peak data rates of up to 14 Mbps in the downlink and 5.76 Mbps in the uplink. Long-term evolution, marketed as 4G LTE, is based on the GSM-Edge and UMTS HSPA network technologies, increasing the capacity and speed using a different radio interface together with core network improvements. The standard is developed by the 3GPP and is specified in its Release 8 document series, with minor enhancements described in Release 9. LTE offers peak data rates of 300 Mbps in downlink, and 75 Mbps in uplink. 3GPP developed specifications for LTE Advanced to meet the International Mobile Telecommunications (IMT) Advanced Requirements for the wireless evolution in Release 10 and beyond. LTE-A allows deployment bandwidths of up to 100 MHz, enabling peak target data rates in excess of 1 Gbps in the downlink and 500 Mbps in the uplink to be achieved. As part of this course module, we shall study LTE Advanced in detail.
In the evolution path, LTE was developed by 3GPP in Release 8. Release 9 introduces some minor enhancements to LTE Release 8 with respect to the air interface. Key technology advancements introduced in LTE are: the LTE adopted orthogonal frequency division multiplexing, OFDM, instead of CDMA as multiple access technology, in order to efficiently support wideband transmission. LTE supports flexible bandwidth ranging from 1.4 MHz up to 20 MHz. LTE technology based on fast CQI-based link adaptation, turbo coding utilized together with hybrid ARQ retransmissions and use up to 4x4 single-user MIMO support in downlink. With these features, LTE Release 8 supports peak data rates exceeding 300 Mbps in downlink and 75 Mbps in uplink, and a cell average spectral efficiency gain of 2 to 3 times over HSPA Release 6. The LTE network architecture, like any other mobile network, consists of three key components. User equipment called UE, access network, which in LTE is called Evolved UMTS Terrestrial Radio Access Network, EUTRAN, Packet Core Network, Evolved Packet Core, EPC. They work together to provide connectivity, mobility and services for mobiles. At a high level, the network is comprised of the core network, EPC, and the access network, EUTRAN. While the core network consists of many logical nodes, the access network is made up of essentially just one node, the evolved node B, eNode B, which connects to the UEs. Each of these network elements is interconnected by means of interfaces that are standardized in order to allow multi-vendor interoperability. This gives network operators the possibility to source different network elements from different vendors. A departure from pre-4G architectures, the EUTRAN is notably missing a controller. All of the radio access network functions are distributed to the cell site equipment, the evolved node BS, ENBS. The term LTE encompasses the evolution of the Universal Mobile Telecommunication System, UMTS, radio access through the evolved UTRAN, EUTRAN. It is accompanied by an evolution of the non-radio aspects under the term System Architecture Evolution, SAE, which includes the evolved Packet Core, EPC, network. Together LTE and SAE comprise the Evolved Packet System, EPS.
Release 10 LTE Advanced is not a new technology but an evolution of LTE Release 8. Significant features are added into LTE Release 10 in order to meet IMT Advanced Requirements. All existing LTE Release 8 and Release 9 requirements are equally applicable to LTE Advanced. Release 11 introduced some enhancements to Rel 10 LTE Advanced. LTE Advanced meets or even exceeded the requirements defined by IMT Advanced. So, overall LTE Advanced is a superset of requirements defined in LTE Rel 8 and IMT Advanced. Some of the key requirements for LTE Advanced are: peak data rate. The system should target a downlink peak data rate of 1 Gbps and an uplink peak data rate of 500 Mbps. Transmission bandwidth. LTE allows scalable bandwidths of up to total of 100 MHz as against 20 MHz in LTE Release 8. Latency. On control plane, the target for transition time from idle mode to connected mode should be less than 50 milliseconds, while on user plane LTE Advanced should allow for reduced to-plane latency as compared to LTE Release 8. Spectrum efficiency. LTE Advanced aims to support downlink peak spectrum efficiency of 30 bps and uplink peak spectrum efficiency of 15 bps. Mobility. The system shall support mobility across the cellular network for various mobile speeds up to 350 km per hour, or even up to 500 km per hour depending on the frequency band. LTE Release 8 defined 5 UE categories, namely Class 1 to Class 5. Out of these 5 UE categories, Class 3 and Class 4 category UE shall be used as commercial LTE devices now and in near future. Independent from the LTE Advanced technology components, new UE categories 6, 7 and 8 are added into LTE Release 10. These categories describe to a certain extent the device's capabilities. For instance, categories 6 and 7 support MIMO 2x2 and or 4x4 and go up to data rates of 300 Mbps in downlink. Whereas category 8 is the highest category, supporting 8x8 MIMO leading to a peak data rate of 3 Gbps. Uplink category 8 leads to 1.5 Gbps data rate using 4x4 MIMO and 64 QAM modulation. The UE category is only an indication of the user device's capabilities. It is used as kind of an upper bound for achievable data rates. UE capabilities are exchanged between the network and UE during the initial attach procedure. Attach procedure in LTE Advanced is unchanged compared with LTE Release 8. After EPS bearer setup and during the UE capability transfer, the device identifies itself as LTE Release 10 capable by providing additional information on top of the standard LTE Release 8 capabilities.
LTE Advanced doesn't change the high-level LTE Release 8 network architecture. LTE Advanced benefits from technology evolution in baseband and RF area, the new available spectrum and the optical fiber availability. LTE Advanced for meeting the IMT Advanced requirements introduced important technology changes to enhance macro network performance and enable efficient use of small cells. Some of the important technologies of LTE Advanced that we would study as part of this course include the following. Carrier aggregation enables improved peak data rate and throughput scaling with aggregated bandwidth. Enhanced MIMO enables higher peak data rate and spectrum efficiency through scaling with antenna paths for urban grid and small cells. Coordinated multipoint capacity and cell edge performance enhancements by active interference cancellation. Relaying enables focus coverage extensions with small cells by self-backhaul. Heterogeneous networks enables focused capacity enhancement with small cells by interference coordination. Let us now study all of these LTE advanced enhancements in more details. One straightforward possibility to reach high data rates requirements is to aggregate multiple LTE carrier. Two or more component carriers, CC, are aggregated in order to support wider transmission bandwidths up to 100 MHz with a maximum of 5 component carriers. LTE Release 8 terminals can only transmit on one component carrier, whereas LTE Advanced terminals may transmit on multiple component carriers simultaneously to reach the higher bandwidths. In this figure, LTE Release 8 terminals, UE1 and UE4 transmit on one component carrier. LTE Advanced terminal, UE3 transmits on 2 component carriers and UE2 transmits on 3 component carriers. There are 3 types of carrier aggregation. 1. Intra-band contiguous carrier aggregation. In this 2 or more continuous component carriers, CC, within same frequency band may be allocated to LTE-A. This applies when an operator owns a wide available frequency band. 2. Intra-band non-contiguous carrier aggregation. In this 2 or more non-continuous CCs within same frequency band may be allocated to LTE-A. This scenario will be useful when some unavailable range exists within the LTE Advanced working bandwidth. 3. Interband non-contiguous carrier aggregation. In this 2 or more CC from different frequency band may be allocated to LTE-A. This scenario is the most attractive to operators, since it allows combining CCs distributed across different bands. Carrier aggregation enables high data rates through increased bandwidth. In addition, it can be used to effectively support different component carrier types that may be deployed in heterogeneous networks. Carrier aggregation is attractive because it allows operators to deploy a system with extended bandwidth by aggregating several smaller component carriers while providing backward compatibility to legacy users. The component carrier set is UE-specific. UE registration with the network always takes place on the primary component carrier or PCC in both uplink and downlink. Additional bandwidth is provided by secondary component carriers or SCC with a maximum of 4 SCCs. In downlink direction, PCC carries both PDSCH and PDCCH, while on SCC, PDCCH allocation is optional. In uplink direction, the PCC carries PUCCH and PUSCH while SCC only carries PUSCH. Handover and ratch procedures are only executed on the PCC. On the radio link control (RLC) layer, there is only one connection per UE independent of the number of component carriers assigned. Multiple CCs are handled on the medium access control (MAC) layer. There are separate HARQ transmissions/acknowledgements and data modulations for each CC. The UE provides individual channel state information (CSI) reporting for each individual CC.
Multiple input multiple output or MIMO refers to a communication system that is equipped with multiple antennas at both transmit and receive sides. LTE Rel supports 2x2 and 4x4 MIMO schemes on downlink. LTE Rel does not support MIMO in the uplink. LTE-Advanced extends the MIMO capabilities of LTE Rel to now supporting 8x8 MIMO in downlink and 4x4 MIMO in uplink. In LTE-Advanced uplink direction, the same principles as defined in LTE Rel downlink apply, whereas, in LTE-Advanced downlink direction the existing LTE Rel scheme is extended. The maximum spectral efficiency defined as 30 bps in the downlink with the use of 8x8 MIMO spatial multiplexing and 15 bps in the uplink with the use of 4x4 MIMO spatial multiplexing. When the UE moves to the cell edge, it will communicate with more than one ENBs to prepare for handover. This is also the time when the UE receives strong interference, and data rate will be very low. LTE Coordinated Multipoint or COMP is a method of transmitting to or receiving from a user equipment using several base stations. Essentially, LTE COMP turns the intercell interference into useful signal, especially at the cell borders where performance may be degraded. It results in enhanced UE performance even at cell edges. Coordinated multipoint can be applied to both the downlink and uplink. DL COMP can be classified into two techniques. 1. Joint processing. 2. Coordinated scheduling coordinated beamforming. CSCB. In coordinated scheduling coordinated beamforming, CSCB, a given subframe is transmitted from one cell to a given UE. Coordinated scheduling and beamforming is done between cells to reduce interference caused to other cells. Coordinated scheduling coordinated beamforming, CSCB, can be realized only if the channel state information and scheduling information are shared among ENB. Joint processing is available when neighboring cells share transmit data as well as the channel state information. The joint processing can be realized in the form of joint transmission or dynamic cell selection. In joint transmission, cooperating ENBs jointly transmit data to one or more corresponding UEs. Dynamic cell selection is a kind of fast cell selection. UEs are handed over to the best cell considering interference situation. Joint processing generally requires high-capacity X2 interface between ENBs for sharing transmit data, and thus can cause excessive backhaul overhead and latency. For the uplink, LTE COMP, coordinated multipoint requires the application of the relevant signal processing within the receiver. It is very similar in concept and application to the macro diversity schemes used in previous cellular systems. The concepts of this are well established.
With an explosive growth in wireless traffic, a variety of small-size low-power base stations are being deployed within the usual macro ENB to serve hot zone, office, and home areas. This type of overlay architecture is referred to as heterogeneous network. Different types of nodes are optimized for better coverage and data transmission. These are networks which are built up by a macro cell, MC, to ensure coverage, and by picocells, PC, and femtocells, FC, to illuminate shaded regions or to enhance the data rate in hot spots. all cells are using the same frequency and more severe interference scenarios do exist compared to single-layer deployments. The idea of heterogeneous network is in itself not new. It is a deployment strategy and not a technology component. As such, heterogeneous deployments are possible with LTE Rel 8 and Rel 9. However, Rel 10 provides additional features that improve the support for this type of deployment. LTE Release 8 Intercell Interference Coordination (ICIC) methods are mainly targeted at improving radio resource utilization of cell edge users. Traditionally in UEs, the node selection strategy was based on downlink signal strength. Typically, there are two borders to the picocell, PC/femtocell, FC, the conventional cell edge where the downlink signal from the PC is the strongest one, and a so-called cell range extension, CRE, where the path loss on the uplink to the PC is still smaller than the path loss to the macrocell, MC, whereas the downlink signal from the MC is the stronger one. The reason behind this asymmetry is the difference between the transmission powers, which is usually much higher for the MC compared to PCFC. LTE Release 10 uses the concept of range expansion to increase uptake area of a low-power nodes such as femtocell or picocell. The advantages of this technique are enhanced uplink data rates, by at least partially taking uplink path loss into account when associating terminals with a low-power node. Increased capacity, receiving downlink traffic from the low-power node even if the received signal strength from the macro is higher allows for the reuse of transmission resources across low-power nodes. Improved robustness. Enlarging the coverage area of a low-power node can reduce its sensitivity to ideal placement in a traffic hotspot. LTE Advanced extends LTE Release 8 with support for relaying in order to enhance coverage and capacity. UEs communicate with a relay node, RN, which in turn communicates with a donor E node B, DENB. Relays can be used for improving the signal-to-noise ratio conditions at cell edge with low additional infrastructure cost. Relays are being considered for LTE Advanced as a tool to improve cell edge performance and fill coverage holes. In the LTE Advanced, two types of relay node, RN, are defined according to the functions and supportable protocol layers. A Type 1 relay node, RN, creates its own cell, that is transmits its own cell ID and own synchronization and reference signals. The UE communicates only with the RN and is oblivious of the donor ENB. So, from an UE perspective this Type 1 RN looks like a conventional E node B and cannot be distinguished from it. A Type 2 relay node, RN, does not have its own cell identity and is part of the donor cell. The Type 2 RN just helps the donor ENB and UEs transmit data. Control signals are transmitted directly from the ENB to UEs. Type 2 RN can transmit PDSCH but it does not transmit CRS and PDCCH. It is transparent to Release 8 UEs. A Release 8 UE is not aware of the presence of Type 2 RN.
This completes the module.